Hey guys, hope everybody's doing all right. Today's Friday. Well, actually, it's Thursday night, but it's going to be Friday. I guess when you guys watch this, there was a mix-up on the last videos. I don't know what happened, but it didn't get posted to YouTube. I think until this morning. So sorry about that, and I'll try to make sure it doesn't happen again. Okay. Oh, and then the other thing was I put a new homework assignment in the Dropbox. So, and it's due, I think, maybe a week and a half from now. So, if you have any questions or anything like that, don't hesitate to let me know. Okay. All right. So last time we were finishing up our discussion on degenerate or non-degenerate, basically time-independent perturbation theory. And we had started to talk about hydrogen-like atoms. So these are atoms that have any number of protons, but they've been stripped down to only one electron. And what we were looking at were what are called fine structure corrections. So, we know how to solve for the energy levels of the unperturbed hydrogen atom. What we were looking at last time were some small corrections onto those energy levels. And we started out by looking at corrections from accounting for the fact that the electron is relativistic. It's moving, with relativistic speeds. And so what we did was we took the full relativistic kinetic term and expanded it out like you usually do, but instead of dropping the second order term or the p to the fourth term, we kept it and we treated it as a perturbation. And we went through and we computed the corrections to the first order to the energy. So we computed the corrections up to first order in this perturbation. Along the way, we had to use some tricks. I won't go through all those again, but in the end, where is it? Let's get there. So in the end, we found that the corrections from treating the electron relativistically go like alpha squared times the normal energy. Okay, and they scale like 1 over n to the fourth, and then there's a 1 over n cubed term. All right, and we made sure that this made sense by saying, in the semi-classical or semi-quantum picture, the electron's velocity is typically on the order of alpha, so the beta factor is on the order of alpha, and so it makes sense that since we're considering a beta squared type of correction, that it makes sense that this is an order alpha squared correction to the first order energy. Okay, so then the next thing we did was to talk about the spin-orbit interaction. And so this is a correction coming from the electron moving in the Coulomb field, and to the electron, it's actually the proton that's moving, and so the protons are charged, and so they're creating a magnetic field. And this kind of effective magnetic field is going to interact with the intrinsic spin or the intrinsic magnetic moment of the electron. And so we started by trying to guess the form of the Hamiltonian, the piece that we want to add to the Hamiltonian. And we found that our guess was almost correct. We were only off by a factor of 2. And this factor of 2 comes from something called Thomas precession. And we'll get into that later when we get into relativistic quantum mechanics and talk about the Dirac equation. But basically, the correction coming from this looks like a dot product between the orbital angular momentum and the spin angular momentum. And then depending on what type of central potential you plug in, it's a derivative there, but that's just a constant term, so it's fine. All right, so what we did was we want to treat this as our unperturbed Hamiltonian, right? And then treat this HLS as our perturbation term. And when we look at this operator, we see that it depends on the dot product of L and S. And so we ask ourselves, well, what basis do we want to work in? Do we want to work in the uncoupled basis, where L squared, LZ, S squared, SZ are the good quantum numbers, or do we want to work in the coupled basis where L squared, S squared, and then the total angular momentum J squared and JZ are the good quantum numbers? And it turned out that both sets are satisfactory in the sense that they'll give you the same answer. At least they should, but one's easier than the other. And so it turned out that the second choice, which was the coupled basis, turns out to be the advantageous one for us to work in. So in this coupled basis, we can write down the wave function. It's just the radial part times these what are called spin angular functions. And their spin angular functions are just basically spherical harmonics with some coefficients that depend on the L and M quantum numbers. And so what we had to do was compute because this guy is already diagonal, so we don't have to worry about applying degenerate perturbation theory. We can just apply non-degenerate perturbation theory. So all we really need to do is compute the matrix element, or the expectation value of this operator. And when we do that, so the tricky part was doing this this angular integral, right? But it's not that bad. You can rewrite the L dot S in terms of J squared, L squared, and S squared, and then have those guys operate, and then use the orthonormality of the spin angular functions. Okay, so we were able to get down to that answer, and then finally we could put everything together and have the first order energy shift, and this is known as Landé's interval rule. Okay, so this is for a generic central potential, and so we can plug in. So remember, so we still need to compute this expectation value here, and so what we want to do is plug in the Coulomb potential and try to compute that guy, and that's where we use some more tricks. Okay, I'm not going to go through them again, but in the end, we were able to compute that expectation value, and then finally we put it all together, and we got what's called the fine structure, fine structure type of correction. Okay. All right. So today I want to finish off this discussion. It won't be nearly as long of a lecture, but I want to. I don't want to go long because after this we go into time-dependent perturbation theory, and I don't want to start it and then have to quit after a couple of slides. So this lecture will be a little shorter, and then Monday's lecture we'll start with time-dependent perturbation theory. Okay. All right. So what we want to do now is consider something. It's called the Zeeman effect. This is a case where you take a hydrogen-like atom, and let me make this bigger. Where you take a hydrogen-like atom, and instead of putting it in an external electric field like we did for the Stark effect, here we can put the electron, or the hydrogen-like atom, in a uniform external magnetic field. Okay, and I'll denote that by B. And so before we get into how do we write down the interaction term between the electron and this external field, it kind of it's advantageous for us to take a step back and remember our classical E and M, even though you might want to forget it, but you always have to remember it. And the idea that we want to use is that the magnetic field can be derived from a vector potential, right? And that vector potential, we can actually invert it and write the vector potential in terms of the magnetic field. Okay, so if we wanted the magnetic field, say we want to align it in the z direction, then we could actually accomplish this by writing down a vector potential that has components in the x and the y, right? Because this thing is going to get crossed. Because when I take the curl of this thing, which is going to give me the magnetic field, it'll give me back out a magnetic field pointing in the z direction, right? Okay. And you might ask yourself, why are you doing this? Well, it turns out that anytime you have a magnetic field involved in quantum mechanics, and you want to write down the interaction of, say, an electron with this external magnetic field, you can use an idea, I think it goes back to Dirac, but it's called minimal coupling, right? And so if you have a Hamiltonian for a free electron, and then you put it in a magnetic field, you can actually quickly write down the Hamiltonian by using this idea called minimal coupling. And we'll talk about it in detail when we get to relativistic quantum mechanics. But for now, let me just say that the way that you do this is the only thing you have to do is take your momentum and the what do I call it, non-interacting Hamiltonian, and replace it with the momentum minus this factor of E over C times the vector potential. And this is something maybe you've seen this before, but sometimes people haven't, so don't feel bad if you haven't. Okay, but like I said, we'll talk about it in detail when we get to relativistic quantum mechanics. Okay, so we want to take our this Hamiltonian here, right, and plug in this redefinition of P, right? And when I do that, so I get the P squared term back out, I get my central potential piece. But then when I square this guy, I get some cross terms between P and A. And remember, these are operators, so we have to pay attention to the order. And then there's an A squared term, okay? And right. So if you remember when we talked about back when we first introduced the ideas of potentials and working in position space, we said that we would always assume that our potential is diagonal in position space. In other words, there's no off-diagonal terms if we were to write this operator down in matrix mechanics, right? So this is an assumption that we always make, right? So that means that if I want, I can use a little trick here. Okay, so let me denote. This is supposed to be like an empty ket, and when it's empty like that, it just means that it's any ket. It's totally arbitrary. Okay, and so what I'm going to do is use this trick and say, okay, so let me sandwich this operator between any ket and from the left and eigen bra from position space. Okay, and you say, well, why would I want to do that? Well, let's just see. So we take P, we rewrite it in terms of its position space, right? And then we use that nice identity that says anytime we have this guy, we can pull that derivative outside, right? And once we pull the derivative outside, then A, which is just a function of x, can hit this x prime bra and gives us the number, right? Or it's really a vector, but it's not an operator anymore, okay? So now I can take this guy and let it operate, right? So what I'm doing here is, let's see if I can get this right. So this is obviously the term that's operating on where the derivative's hitting this guy, right? And then the other term would be, right, it would be the derivative hitting this guy, right? But the derivative hitting that guy I can rewrite in terms of my momentum operator, right? And then A, I can pull back inside because, and make it an operator again, because now I have this A of x prime, it's just back to an operator, right? And you convince yourself that this term will give you that second term from taking the derivative. Okay, if that doesn't make sense, rewind it and listen to it over and over again, and hopefully I'll start making sense, okay? Or just work through it yourself, okay? That's probably the best thing to do. Anyways, okay, so what we have is this relationship between this thing and these things on the left and right, right? And what I see is that when the divergence of A, so this term right here, when this vanishes, I'm left with this thing equal to that thing, right? And then when I have that, I can take the bra and the cat away, and I find this operator relation that says that P dot A is equal to A dot P, right? And that'll simplify, if you look back here, we have this cross term, right? So that'll allow us to combine those two terms if that was the case, right? And luckily, if you remember from E&M, you always have a freedom and the gauge, the choice of the gauge, right, that you choose for your vector field, right? And so the gauge where the divergence of the vector potential vanishes is called the Coulomb gauge, and it's typically the one that you work in. But there are other possibilities, and maybe you've had fun exploring those in your E&M class. Okay, but for us, let's just work on the Coulomb gauge, because then this thing will vanish and we can combine those two terms in the Hamiltonian. Okay, so now we can, so now we just have one term, this P dot A, right? And I can now plug in my A that we had written down before that gives us a magnetic field in the Z direction, and take the dot product, okay? And so what I get is something that looks like this, so it's minus 1/2 B, and then I get this combination of YPX minus XPY, and that's just the angular momentum operator, orbital angular momentum operator in the Z direction, okay? All right, so finally, and then the A squared term that's in our Hamiltonian, so this guy, we can square it out. We can, write it in terms of the magnetic field and square it out, and we find something that looks like this. Okay, so now we can combine it all, right, into this one Hamiltonian. Okay, so we still have our unperturbed guy, and now we have these two pieces coming from the interaction of the electron with the magnetic field. All right, so it turns out there's one other part that we still need to add in, and that's due to the interaction of the electron's spin or magnetic moment with the magnetic field. All right, and so this is similar to the correction that we talked about last time, but here magnetic field is a real magnetic field. It's external magnetic field. Okay, so we're going to have a term that looks like minus mu dot B, and we know that mu we can write in terms of the spin operator, right? And if I dot S into B, B is pointing in the Z direction, so that tells me that S, the only component of S that contributes is the SZ component. Okay, so all right, so we're going to add this term into our Hamiltonian, but luckily for us, these quadratic terms, it turns out that they're negligible. Okay, I don't want to spend time going through and trying to compute them to show you that, but let's just take it for fact that these guys are negligible compared to the other operators. Okay, and so what we'll do is we'll just drop this term. Okay. All right, so that means that I have this stuff, these first three terms, and then this term, right? And actually, I can write this in terms of three distinct terms. Okay, so we have our original Hamiltonian. We've got we got the Hamiltonian coming from like a spin-orbit coupling, right? And then we have, so this is the correction that we considered last time, and this is the correction that the new piece of the Hamiltonian that we were just considering. Okay, so here's the piece coming from the orbital, and here's the piece coming from the spin. Okay, so this is, so we've got, again, the unperturbed piece. This is coming from that spin orbit correction, right, that we talked about last time, and this is coming from our external magnetic field. Okay, so this is the problem that we want to solve, and how you go about solving it really depends on the strength of the magnetic field. Okay, so you basically have two options in this case, right? So there's what we call a weak field limit, right, and this is where the magnetic field is relatively small, right? And so what happens is this HB term is small compared to these first two terms, right? And so in that case, you can treat HB as a small perturbation on the unperturbed Hamiltonian of the combination of H0 and HLS. And then you have what's called the strong field limit, and in that case, this guy starts to dominate over the spin orbit spin orbit interaction, and so we treat the spin orbit interaction as a perturbation on H0 plus the HB term, right? So those are our two choices. So let's look at the weak field case first, okay? And what we want to remember is last time we saw that in the coupled basis, the unperturbed Hamiltonian and the spin orbit Hamiltonian are diagonal in this coupled basis, okay? So it makes sense to rewrite this HB in the coupled basis, right? Remember, in the coupled basis, the good quantum numbers involve the J, right? The J total angular momentum. All right, so what I want to do is I want to take this piece of the operator, the LZ plus 2SZ, this guy, and rewrite it in terms of the total, right? So I can do that by just splitting up the 2SZ into SZ plus SZ, and then taking LZ plus SZ to be JZ, okay? All right. So that means now we can compute the first order energy shift coming from this term, right? So this will be an energy shift on top of what we computed last time, right, for the spin orbit piece, okay? So we just need to compute this thing, right, this expectation value in the coupled basis, and the JZ piece is easy, right, because JZ, here's what the JZ quantum numbers are, yeah, it's this M, right? But the SZ is a little tricky, right, because the SZ is a good, its quantum numbers are good quantum numbers in the uncoupled basis, right? So what we have to do is, in order to compute this expectation value, is to do a transformation from the coupled basis to the uncoupled basis, right? And then let that SZ operator operate on those states, and then and then dot it all out, right? So what I would do is I would want to rewrite these states, the coupled basis states, in terms of the uncoupled basis states, right? So where I have these states are the uncoupled basis states, right? And the prefactors are what we call the Clebsch-Gordon coefficients, okay? But once you write that out, then this SZ operator can hit these guys, and it's going to pull out a H bar over 2, right? And then you multiply everything out, and you use the orthonormality of those uncoupled basis states, and you find that the expectation value of SZ in the coupled basis looks like this, where these C's are just those the factors here out in front. And if you square them and simplify everything, you find that the expectation value of SZ is just mh bar over this factor of 2L plus 1. Okay, and so now we can put this together with the JZ expectation value and find the first order energy shift in this weak field limit. So this, again, will be the correction on top of that spin orbit correction that we computed last time. Okay, so that's the weak field case. In the strong field case, it actually works best for us if we work in the uncoupled basis, right? Because in the uncoupled basis, this HB, which is, again, the dominant term now, is easy to compute, right? Because it goes like LZ plus 2SZ, and so when we compute the expectation value, I don't know if you guys can hear that, but somebody above me is vacuuming, and it's driving me nuts. But anyways, I lost my train of thought. But so we choose on a couple basis, right? And that makes this operator easy to compute, right? So what we have to do now is compute this the spin orbit operator in the uncoupled basis, right? And to do that, we can actually use a trick where let me dot these guys out, right? And then remember that LX, LY, SX, SY, they can be written in terms of raising and lowering operators, right? And so what we find is that these terms you can write as 1/2 times this stuff, right? And you know that this stuff is going to give you 0 contribution, right? Because it's an expectation value. So this S plus is going to try to raise this MS value, and then you would have two orthonormal states. You would have two orthogonal states, and that would give you 0, right? So, and likewise for this S minus operator. So the only thing that survives is the LZ SZ term, and that thing is easy to compute in the uncoupled basis, right? It's just ML times MS. Okay, and so what you find is that the first order energy shift in the strong field limit boils down to this, right? And all you have to do again is compute this expectation value. You just plug in your central potential, and then you would have your correction. Okay, so it's you would use the same tricks that we used back when we computed this thing last time. Okay. And then, so finally, I just wanted to show you some pictures of the Zeeman effect. So this is, these are just pictures I pulled off the web. So you can see this is a case where you have, before the magnetic field, you have two states, right? An L equals 1 state and L equals 2 state. And this is showing, the energy difference between the two. So if you had an atom in this state and it would drop down, it would emit a photon with an energy of h nu, where nu is the frequency. And then when you apply this magnetic field, you find that the L state splits into 3 states. So the M equals 1, 0, minus 1. And the L equals 2 state splits into its 5 components, right? And so what you would see is that, you would apply the magnetic field and then excite the atom, and you could read off all these, you would see photons with all these different energies. Okay. And then finally, this is just a picture that I thought was pretty cool. It shows in the weak field limit, this how the splitting works, right? And in the weak field limit, I think they're using a different basis than us, but the point is that the basis changes as you go from the weak field to the strong field, right? But you can see that the kind of the magnitude of the splitting grows with the strength of the magnetic field. Okay, and that's for, I don't know what RB is, rubidium. I have no idea. But anyways, so that's it for time independent perturbation theory. Next time we'll start to explore the wonderful world of time-dependent perturbation theory, and that's where things get a little hairy, but we'll work through it, and that'll take us right into scattering theory. Okay, so everybody have a good weekend. Let me know if you have questions about anything, and I'll see you on, I guess, on Monday. All right. Have a good weekend.